So, hello students, welcome back to this lecture series on VLSI design KEC 072. This is lecture number 16. I am Dr. Raman Kapoor, Associate Professor at Department of ECE AVS Engineering College. We continue with our discussion on sequential CMOS logic design. Consider this lecture as part 3 in that series. At the end of my last lecture, I had introduced the implementation of a D type latch. Okay. That was a level triggered circuit in such a way that when the level of the clock or enable is either 1 or 0, depending upon that a particular input enters the latch circuit. Okay. In that, what we are doing basically was we were multiplexing the inputs available at the latch circuit. Okay. By multiplexing, we mean a selection circuit or a circuit which is selective in nature in such a way that it selects a particular input depending upon the selection lines. Okay. So, using that as a base or a background, let us see how latches can be implemented in a multiplexing fashion. These are known as so called multiplexing transmission gate latches. Okay. The idea is still the same, the objective is still the same, that we want to design a storage circuit, a memory circuit for a sequential design, so that the current state can be stored to decide the next state. Okay. So, here I have shown you a circuit or a schematic symbol of a transmission gate. Okay. So, you have a PMOS here, you have an NMOS here, the gate electrodes are here, A is input and B is output. Okay. If I apply a high signal at the gate of NMOS and the complementary of that, which means a low signal at the gate of PMOS, this transmission gate turns on. Okay. So, suppose G is 0 and this G B is equal to 1. In that case, the NMOS is off and PMOS is also off. So, this is a open switch. The opposite case, when G is 1 and G B is equal to 0, okay, both NMOS and PMOS become on. So, this is now a closed switch. The output always takes the same value as the input. There is no toggling or there is no other logic operation in the middle. The output is always going to follow the input and the input is transmitted with equal strength either way. If it is a 0, it is still passed equally well as a 1. This is the main advantage of having a transmission gate, and these are some of the symbols which we use in circuits. The first symbol is the most common for a transmission gate. So, what it basically is doing is it is implementing the multiplexing operation only. Okay. It is performing a selection case only via a switch, and this multiplexing operation can be implemented to obtain the latching operation also. So, here if you see, you have one transmission gate here which is being driven by an inverter. This transmission gate has clock connected to PMOS and complementary of clock connected to NMOS. You have another transmission gate here whose PMOS is being controlled by complement of clock and the NMOS is being controlled by the clock signal as it is. Okay. So, when clock is 1, if clock is 1 here, so this becomes 0 and this is 1. So, this is off, this part is on, here it is on and this is on, which basically means that this transmission gate at the bottom, the lower transmission gate or the lower switch turns on or becomes a closed switch. In that case, this D complemented here by the inverter will enter this circuit. So, D bar will be allowed to enter, again gets inverted and Q gets updated by D. This is known as a so called write operation of the latch circuit. So, the output takes the value of the input. Vice versa, when clock is 0, you get a 1 here which is clock bar and you get a 0 here. So, this NMOS is off, this PMOS is off, but this NMOS is on and this PMOS is on, which means that this transmission gate now turns on and this is still off, this is now off. Okay. So, whatever is available here and what is available here via regenerative feedback or positive feedback, Q is being fed back here. So, Q comes here and Q bar comes here. So, Q bar is being fed and again it gets inverted here and Q remains same. So, what is happening here? The hold operation is taking place, the storage aspect of a latch circuit is taking place. Okay. So, depending upon the inputs to the clock, you can replace the clock with an enable signal also here, you can make it active high, you can make it active low. Okay. In that case, you can implement this latching circuit and again this is still a level triggering circuit. Now, let us proceed to another topic. We have done the latching aspect of sequential circuits, but there is a small problem to that. Latches are always level triggered. Okay. These two figures at the top, this circuit is triggering when clock is high, level is high. This circuit is triggering when the level of clock is low. During this duration, when the clock is high or during this duration when the clock is low, if the input changes its value, the output will definitely change. Okay. Now, that is something which restricts the user control or the designer's control on the circuit. This is not a circuit which is known as a edge triggered circuit, this is a level triggered circuit, and if this time period is very large, some noise at the input can also cause your output to change and resulting in an unreliable erroneous output. Okay. To solve this problem, we use what is known as edge triggering, which also saves some energy because the power is only consumed only at the time of pulse trigger. So, suppose this is a positively edge triggered circuit. So, when a clock makes a transition from 0 to 1, only then your output changes. Now, till the next trigger arrives, the input can take multiple values. There can be effect of noise also at the input, but the output will remain in hold state. Okay. Similarly, this is a negatively edge triggered circuit, the differences being that for negative edge triggering you use a bubble in the symbol here. So, when a clock makes a negative trigger from 1 to 0, okay, only then the output gets updated. Until the next trigger arrives, till then there will be no updation of the output. This is known as edge triggered devices and they are popularly known as the flip flops. Each flip flop can store 1 bit of data. So, for n bits of storage you need n number of flip flops. They can be synchronized together in parallel in such a way that a single clock trigger, single pulse at the clock or enable can actually update the content of a large number of n number of flip flops. This is a major difference between a latch and a flip flop. Flip flops are the most basic storage element of any sequential circuit. Okay. So, let us proceed further. How to implement edge triggering? Okay. We have seen level triggering circuits, which is very simple. You connect some extra CMOS circuits, you add extra transistor N type and P type, connect the clock or enable as it is to the gate electrodes of those transistors. In that case, for whenever the level is present, active level is present, okay, at the clock, the latching operation will take place. But how to implement edge triggering? Okay. For edge triggering, a very common approach is what is known as a master slave configuration, which is nothing but a collection of two latching elements or two flip flops connected in series. One acts as a master and another acts as a slave. So, here the circuit which is shown on your slide, between dotted lines, between these broken lines, you can see two separate elements connected together. Okay. So, this is a one JK latch, clocked JK latch. Okay. So, you see a clock signal here, J input, K input. This element is now acting as an input to the second element. Okay. So, the operation still remains the same, the characteristic table or the truth table of a JK flip flop does not change, everything remains same, except that you use two similar elements in series. One is known as master, another is known as slave. The master is being driven by the primary inputs J and K. The output of the first stage or the master stage acts as input to the slave stage, and the final output is being taken from the slave stage. Okay. So, the primary input is going to the master and the primary output is coming out of the slave. Okay. So, this cascaded arrangement, so called master slave configuration, is what is used for edge triggering. Okay. Let us see how it works. The input latch is your master stage. Suppose when clock is high or logic 1, when clock is 1 here, I am talking for all the explanation, I am considering the positive edge triggering. When clock goes from 0 to 1 here, whatever is available at J and K, and initially whatever was available at Q and Q bar, all these three signals are used to generate some output here. Okay. So, let us call this as Q M and call this as Q M bar. Okay. This output acts as an input here. Now, the design is in such a way that these two stages, although they are similar in every respect, they are similar in terms of connections and circuits, but they are completely isolated from each other, and the second stage is actually isolated from the primary input also. Whatever is happening on the primary side will not affect the second stage. Why? Because of this inverter here. If this is triggering at positive edge, this will trigger at negative edge. If this is triggering at negative edge, this is going to trigger at positive edge. Okay. So, they are, this is again an interesting way to use the complementary nature of logic circuits. Okay. Now, when Q M or Q M bar are generated, when the clock changes its polarity, okay, when it goes 0 here, it will show a 1 here. Okay. Now, this triggers. Now, this circuit is cut off. Now, the first stage is completely cut off. Only the second stage is working. Now, this is triggered, but for this the input is coming from the second stage, it has nothing to do with the primary input. So, now you see why it is called edge triggering. For this duration of the clock pulse, when the master stage is inactive, you can have any number of changes in the primary inputs, you can have level changes, the level can still remain 0, the level can remain 1 after the inverter, but any change in the input will not affect your output, because this stage is now cut off. Now, depending upon Q M and Q M bar, okay, and this cross connection of the actual output, now your present or next state is going to be decided. Okay. So, for the first half of the clock, I am talking about positive edge triggering. For the first half of the clock, only the master stage is active and it is deciding the input for the slave stage. For the second half, the master stage is cut off and the slave stage decides the actual output of the circuit. So, this way any noise at the input, any changes at the input are not reflecting at the output even if the level is there. So, this way only triggering is taking place at the edge of the clock, not at the level of the clock. Okay. This is the timing diagram. Okay. The first line is a clock, then you have your primary inputs J and K, right. Stages of the master, outputs of the master Q M and Q M bar, and output of the slave Q S and Q S bar. Okay. QS and QS bar is this output here, QS and QS bar. Okay. Let us see how this timing diagram describes the operation. See, when clock is going from 0 to 1 here, okay, clock makes a transition from 0 to 1. Here J is 0, K is 0, QM past output was 0 and 1. So, that is maintained. Okay. When J and K both are 0 0, the previous output is retained. At this stage you see nothing is happening here also. The clock still remains 1, J and K change their stage here. Okay. Here J goes 1 and K remains 0, stage is changed here, input is changed here. This changes its value. Okay. This goes from 0 to 1 and 1 to 0, but see that the output is still not there. The actual output has not changed as yet. The actual output only changes when the clock makes a transition here from 1 to 0, right. When this transition happens, then this input QM bar is used to decide the output of the slave, which is the output of your actual circuit. Okay. So, for the first positive edge triggering, even when the level is high of the clock, J and K input, even if they change, the actual output does not change. So, this way we have actually converted the circuit from a level triggered circuit to a edge triggered circuit. In isolation, a single stage of JK flip flop will be like a level triggering circuit. Connect them in cascade in such a way that the output of first serves as input to the next. Okay. Isolate the output from the primary input, isolate stage 1 from stage 2. In that case, you are only updating your outputs only on edges, right. This way you are implementing an edge triggered device or register known as a flip flop, and this is the most primary storage element in any sequential circuit. Okay. Now, let us see a practical implementation of a JK flip flop. The circuit which you see on your screen is from a circuit of actually a practical IC which is used for implementing JK flip flop operation. Okay. It uses transmission gates. We know how transmission gates work like. They are multiplexing switches. They allow signal to pass through for a particular clock and then they reject signals to pass through at the opposite clock. Okay. In addition to that, we have two more pins. One is known as set bar and reset bar. This bar basically means that the set and reset operation is going to be triggered on active low. Okay. So, when S bar is equal to 0, okay, when this or say when S bar is equal to 0 here, this gives you a 1 here. When this is 0 here, this gives you a 1 here. Suppose if S bar is 0, okay, if S bar is 0, it goes to a NAND gate. If one of the input of a NAND gate is 0, it always gives 1 irrespective of whatever is here. Okay. So, this is going to be X, do not care. So, this is going to set your output at this time, and if this is 0, R bar is equal to 0 or reset bar is equal to 0, one of the input of G4 goes 0, does not matter what is here. Okay. Now, actually we know that 1 is coming here. So, the output of this NAND gate is going to be 0. Okay. So, this is how you can overwrite. Set reset is basically used for initiating logic circuit, for initiating logic design or logic storage. They are some external pins which override or have preference over all other operations. Okay. So, if you want to set the output to 1, you can put S bar equal to 0. Okay. If you want to put R bar or if you want to reset, okay, if you put R bar here equal to 0, this puts a 0 here. Okay. So, this way you can do set and reset operations. Now, let us just see how this circuit is working like. In this way, suppose initially Q is 1, Q bar is 0, suppose J is 1 and K is 0. Okay. This circuit is a commercial positive edge triggered flip flop, JK flip flop. Okay. This is a positive edge triggered JK flip flop. Suppose initially Q is 1 and Q bar is 0. Suppose J is 1 and K is 0. Okay. So, for this NAND gate, second input is Q bar, which is equal to 0. This Q here is 1. There is an inverter here at K at the start. So, for this NAND gate you are having a 0 and 1, sorry. Since this is a inverter, you are going to have 1. For this 0 and 1, the output which is going to come out is 1, the output which is going to come out here is 0, NAND operation, the output which is going to come out here is 1. So, for this transmission gate TG1, TG1 and TG3, these transmission gates are this transmission gate of the master stage, TG2 and TG4 are the transmission gates of the slave stage. This transmission gate has 1 at the input. When clock triggers, or suppose here the clock goes from 1 to 0, negative edge triggering. Okay. See, the circuit is a positive edge trigger device. The output is taken from the slave stage. Slave and master stages are complementary to each other. So, if the overall circuit has to be positive edge triggered, the slave stage should be positive edge triggered. Okay. And since master and slave are complementary, the master stage should be negative edge triggered. So, at negative edge, when clock goes from 1 to 0, this PMOS is on, this NMOS is on. See, there is a buffer here, there is an inverter here. This is not an inverter, this is a buffer here, here is an inverter. Okay. So, at this point at negative edge, this 1 is propagated through. Okay. And we are assuming that set reset are inactive, neither set is active, neither reset is active, okay, because they override everything. So, you are getting a 1 here, you are getting a 1 here also, okay, and this one has propagated to this NAND gate here. Now, at the next clock cycle, at this clock cycle, when there is a positive transition from 0 to 1, okay, and see this here, this logic gate here G1, that has one of the input coming from Q. Okay. So, Q is supplying another input through G1 and Q was initially 1. So, both inputs being 1, this will give you a 0 here. Okay. For this logic gate, same with G2, you are transmitting. Now, there is 1 0 here. When clock goes from 0 to 1, this NMOS triggers, this PMOS triggers. So, this 0 is propagated. Okay. So, this 0 comes here. This S bar is already 1. So, for this NAND gate, 1.0 is 0 is again going to give you a 1. So, when J was 1 here, this has propagated a 1. Okay. This is how on a positive edge triggering things are taking place. When in a JK flip flop, when both J and K are 1 or 0, it should follow the J type input. Okay. Same happens for the Q bar output, it is taking input here 1 and another input is coming from here. Okay. So, this way you are using transmission gate flip flops and you are implementing edge triggering. If you want to implement a positive edge trigger device, okay, ensure that the master stage is triggered on a negative edge and the slave stage is triggered on the positive edge. Okay. So, use transmission gates for that. I have shown an example where this set reset pins are also there. Okay. So, this is a CMOS implementation of a master slave JK flip flop. Same thing you can do with a D type flip flop. Okay. So, suppose D is initially 1, Q is 0. So, Q bar is 1, let us say set is inactive and reset is inactive. This transmission gate master stage, when clock goes from 1 to 0, this is negative edge triggered. Okay. So, this transmission gate turns on, D goes here. So, you get a 1 input here, G1 is coming from reset. So, that is also 1. So, this transmits a 0 here. Okay. When the opposite clock cycle comes, when clock goes from 0 to 1 through this transmission gate, this 0 is passed, S bar is 1. Okay. So, you get a 1 here. This is how on a negative on a positive edge triggering of the clock, okay, data 1 is being written to Q 1. The opposite also true. If D is 0 and Q was 1, it is going to change the output also. Okay. So, the idea is, instead of latching the current state and keeping it latched, the way you are latching onto the data or the output is different. The type of triggering is different. Instead of level triggering, you are actually doing edge triggering. Okay. The benefit is that in level triggering, any changes at the input, desirable or non-desirable, will get propagated to the output. To solve this problem, we use master slave configuration, where instead of 1 there are 2 cascaded stages, so that the stages are isolated from each other, the primary output is isolated from the primary input, any changes in the input do not propagate towards the output. Okay. In that case, you can implement a edge triggered circuit or a edge triggered register known as a flip flop, which eventually works as their storage element in a sequential circuit. Okay. So, with this I come towards the end of today's lecture. I have shown you how multiplexing transmission gates can be used to select which data is going to enter to your sequential circuit. We have seen examples of a JK flip flop and a D type flip flop, how in CMOS combination they can be used to implement edge triggering circuits. Okay? Thank you.